Okay. We're back. Now, remember electron transport chain. This was really important, right? This was the NADH was the carrying the electrons from the food. And now this is where it comes to cytocox 1. FAD came to 2, right? And there is a ubiquinone Q and a cyto C. These are like little shuttlers. They kind of move around and they carry things. And what they found is that the purpose of this whole process is to drive hydrogen atoms into the intermembrane space, out of the matrix. They move out of the matrix into the intermembrane space. So where's the intermembrane space? The intermembrane space is this area here. So the hydrogen atoms are actually here, all kind of in this space here, right? They're all collected in this orange space. I mean, they're pulled out of the matrix into space, and then they run across the membrane. Now remember, it takes about 4 of these guys to make 1 ATP. Okay? And we'll talk about that. All right, so, but each of these pump a lot of, then you may be wondering how many get into this area. Remember, there's thousands of these happening on this all intermembrane space all over there. Now, we're studying ATP synthase and learned, now the ATP synthase is a really complicated guy. We're not going to go too much into that. But that's a major function of electron transport chain. The chain is a converter of the exogenic flow of electrons from NADH to the 2H from the medicator. So it really, the purpose is to convert the flow, use the flow of electrons from NADH to pump the H from the matrix to here. That is the purpose of NADH into the intermembrane space. This way. That's what NADH is actually doing. So the movement of NADH electrons this way is what allows this to happen. This is a very important concept. It's interesting though. There's different points of oxygen right here. This oxygen here ultimately is the collector of the electrons to make the water at the end of the chain, right? So the oxygen is actually made, the water is actually made in the matrix. Okay, and the oxygen's in the matrix part. That's the important thing. And even these guys are in the matrix. The NADH are in the matrix. The Matrix is a movie. Remember Matrix is a movie? Have you seen this movie? You should go see this movie. It's incredible. The Matrix. Anyway, this is all happening in the Matrix. The only thing that's not happening in the Matrix is these boring guys are all hanging out here. These guys all are hanging out. Why are they all hanging out? First of all, they're kind of crazy. They all don't want to be next to each other. They're all positive signs. So there's tons of energy generated when these guys go across. There's like a shooting of, again, the same concept, the ADP. Remember the ATP, the negative phosphates. Here, they're shooting across. This comes across, and then that converts into an ATP, right? So that power flow. And it takes 4 of these powers to eventually turn into an ATP. All right. I think this is pretty boring stuff. I think the numbers are important though. Just knowing the Q and cyto C are just transporters. They move. These guys don't move. The 4, 3, and 2. And the FAD it comes in early, late in the transport system. So that's why it provides a little bit less. It skips the 1. So it doesn't deliver as much H across. So it doesn't provide as much energy. And so why is that important? But we'll get to that a little bit here. But it is this that is hooked up to power cells. Okay, I'm sorry. I'm taking a break. I'm trying to make sure I'm not missing anything. Okay, we're going to go here now. ATP yield per molecule of glucose at each stage of respiration. Remember the two NADHs. Now the NADHs shuttle span membrane. Okay, you can get when NADH comes across the membrane, it can actually become NADH or FADH. Depends on which cell you're dealing with. This is sort of interesting. So the NADH is made from glycolysis can actually turn into NADH or FADH. You're probably like, what the? You're probably swearing right now, and I would too. But bottom line is this: the two NADH you can go directly as 2, or F. It depends on the cell, depends on some issues, but then eventually these guys come over here and join oxidative phosphorylation. Okay. And here pyruvate, remember 2 acetyl-CoAs. Remember acetyl-CoA only has 2 carbons. 2 carbons and 1 acetyl-CoA. And those make 2 NADHs. Citric acid makes 6 NADHs and 2 FADs. 2, 6, so this, and that's really what joins over here. So you get 2 ATPs out of citric acid, 2 ATPs out of glycolysis. Remember substrate phosphorylation. This guy makes about 26 or 28 ATPs, depending on which it is. Is it going to be NADH coming here, FADH coming here? If it's FADH, it's a little bit less. If it's NADH coming over, it's going to be a little bit more. So that's what varies. That's the whole point, is what they're trying to say, is that it depends on which of these two guys come over here, how many more ATPs. You're probably rolling your eyes at this point. Okay. All right. So I think that's fine. But I think it is important to know this part. I think that's pretty interesting. I found this pretty interesting. We know that 1 NADH results in 10 hydrogens transported out across the inner membrane, but the exact number of H that must re-enter the mitochondrial matrix via the end has been debated. Based on experimental data, however, most agree the accurate number is 4 for 1 ATP. So 1 NADH delivers 10. So the 2 electrons pump out 10. So therefore, a single NADH generates enough force for about 2.5 ATPs. How do you come up with that point, 2.5 ATPs? The idea of 1 NADH comes to 2 is that you make about, if there's 4, that means 4H for 1 ATP, and you're making 10, so that's going to be 2.5, right? Because of 10 divided by 4 is about, 4 hydrogens for 1 ATP. That's the whole concept. And you have 10, right? So that's the whole point. So 10 over, reduce that, right? So 2 ATP. And then the citric acid cycle also supplies electrons to transport chain via FADH, but since the electron answer FADH enters later, it only generates 1.5 ATPs. So it's a little bit less. Now, second, so that's why why are the numbers inexact? So there's 3 reasons that there's inexactation. First, phosphorylation and redox are not directly coupled to each other, so the ratio of NADH molecules to the number of ATP molecules is not a whole number. Anyway. Second, ATP varies slightly in the type of shuttle used across. So remember, we had said that NADH is not, the inner membrane is not permeable to NADH. So NADH in the cytosol is segregated from the machinery of the phosphorylation. The 2 electrons from NADH captured glycosyl must be converted into the mitochondria by 1 several electron shuttle systems. Depending on the shuttle system, the electrons are passed either to NAD or FAD. Oh, I see. So the 2 electrons in the NADH captured by glycolysis must be converted into the mitochondria by one of the electron shuttle systems. Depending on the shuttle system, it's either passed to an NAD. So it's not actually NADH traveling across there. It's a shuttle. It's an electron shuttle. So actually what happens is the NADH comes up here, stops, delivers 2 electrons, and then these 2 electrons and the shuttle can go back to this or this, depending on if it's NAD plus or FAD plus hanging out here, whatever it picks up. So remember, NADH is impermeable. That's due to glucose. It can't get in. It can't get in. Only electrons can get in. Now, but inside here, NADH is going on like crazy from the citric acid cycle. But from glycolysis, it can't get in. So that's what it's saying. The mitochondrial inner membrane is not permeable to NADH. So NADH in the cytosol is segregated from the machinery of oxidative phosphorylation. Okay. That's just one annoying point. And another annoying point, that's just that, each NADH that transfers the pair electrons from glucose contributes enough protein to generate about 3 ATP. I thought we said 2.5 ATP. Finally, I said 2.5 to 3. I don't know. But finally, here, each NADH that transfers a pair of electrons from the glucose electron transport chain contributes enough protein for it to generate a max of 3 ATPs. But this number is not exact. There are 3 reasons we cannot exact number. First, phosphorylation, the redox reaction, are not directly coupled to each other. So the number of the redox reactions happening and the phosphorylation are not directly coupled. So okay. All right. So back to this whole concept. Remember we talked about 34%, 32 moles ATP, 686, 7.3. So 34% of potential chemistry of glucose converted to ATP exponent varies under different cellular conditions. Cellular respiration is remarkable. Okay, so the rest stored of energy loss is heat. We talked about that. Maybe beneficial under certain conditions to reduce the efficiency. Oh, this is really important. This could show up as a test question. So this is fascinating concept. I love this question. Brown fat. Okay, bear with me on this one. This question will probably be on your test, maybe. And this is critical. Okay. All right. This is really important. All right. So this will come somehow. Now, a remarkable adaptation is hybridating mammals. Now, their internal body temperature is slightly lower, but they still have to be warm, right? So they have brown fat, which is packed full of mitochondria. The fat is filled with mitochondria, the fat cells, okay? Now, the inner mitochondria contain a channel protein called the uncoupling protein that allows protons to flow down the concentration gradient without making ATP. Be like, why the hell wouldn't you want to make ATP? I thought the whole point is to make ATP, right? But brown fat in the bears when they're sleeping, and they're snoring, and they're sleeping in the caves in the winter, and those brown bears, they actually have brown fat. They have tons of brown fat. And they have tons of brown fat, but they're not generating ATP. What do they want to generate? Well, activation of these protein hibernating fat cells results in ongoing oxidation of stored fats. So basically what they're doing is they're sleeping, they're not eating anything, right? They're not eating. But they have stored fats that they're sitting on, right? They're fatty bears are sitting there. They're only relying, they're sleeping, so the only fuel is from their stored fats. Now, that's generating heat without any ATP production. Why is that important? Because in the absence of what would happen is if you keep making ATP, right, but you're not using the ATP because they're sleeping, would eventually cause respiration to shut down because you're building up ATP. ATP would begin to rise in the bear that's sleeping. So then the buildup of ATP would eventually cause cellular respiration to shut down by regulatory mechanisms that we'll discuss later. So basically the ATP builds up because you're not using it. The ATP actually in turn is going to shut off phosphofructokinase. It's interesting. We'll learn about that. And say, hey, why are you making more ATP? This is you're screwing everything. So this is body fat. So the body fat here is saying we are just going to generate heat with the flow of concentrating without generating ATP. And remember, breaking down the glucose without making ATP still releases a lot of heat. So if you don't make 32 moles of ATP, still making a lot of heat lost, right? So the rest of energy stored in glucose is heat, right? And we lose heat through sweating. Why do we lose heat through sweating? Remember, water has a high specific heat and a high evaporation point. Remember that. You don't remember that's the special thing about water is it has a very high specific heat. I mean, it takes a lot to heat up water, and it takes a lot and then when water leaves, it leaves with a lot of energy when it evaporates, right? And so cools down the water. So it's a very specific feature of water. I know I digress, but it's in your first chapter. And I wanted to make sure I didn't forget about that little point about water. And I thought I would include it here since we're talking about heat so much. Okay, so water has a very high specific heat. Its specific heat is 1 kilogram per gram of mole. Okay, one's considered high. All right, anyway, so it takes a lot of heat to change the temperature of water. So the point is because there's so many hydrogen bonds, and so that's the whole point. Right? So okay, anyway, the hydrogen bonds of water are constantly moving. Okay, now let's go to fermentation. All right, wonder if I should upload this one separately. Did we talk about cholesterol at one time in the membrane? I wanted to make sure I didn't forget about that. I knew there was something I wanted to add in here. 1 second. I know I'm bouncing around, but there was something about the cholesterol that I thought was important for you to know. Do you know about the co-transport system? Co-transport is really important, right? It in co-transport, downhill diffusion of an uphill solution hooked up, right? So it uses the H gradient generated by the ATP power proton pumps to active transport to drive the active transport into the cell. A co-transporter couples the return of H to the transport of sucrose. This we'll have to look that up. I don't know if you need to know that. I might add that on to you later on lectures if I have time before Friday. Okay, we might need to do this. It's sort of important. Sodium potassium pumps are actually really important in medicine. I actually do have to do that. And hypertonic isotonic solutions are important. You know that, right? Water, these will burst. This will shrivel in hypertonic. But there's one thing I want to talk about: is cholesterol in the cells. It's really, actually, I wonder if there's a lot of, I never got into this chapter too much. We better do this chapter probably. There could be a whole bunch of questions on that, and I don't want to miss that section. Always a section that we forget. Always something. Where's that? Anyways, there's something about cholesterol. It's really important to know about cholesterol in membranes and what it does. To give me a second. It's cholesterol in cellular membranes. 127. 127. Oh, yeah, here. This is what I wanted to make sure. Cholesterol reduces membrane fluidity at moderate temperatures. Okay. Cholesterol reduces fluidity at moderate temperatures by reducing phospholipid movement, but at low temperatures, it hinders solidification. So let's say it gets too cold outside. Actually, the cholesterol is a protector. It prevents it from solidifying, but it also keeps it from getting too fluid. It's kind of like a buffer. So it reduces membrane fluidity at moderate temperatures, but it keeps it from solidifying in the really cold temperatures because it disrupts the packing. So it disrupts the packing. So that's why I wanted to make sure that remember that steroid is wedged between the phospholipid molecules in the plasma membranes of animals, has different effects on membrane fluidity at different temperatures. So I thought that was kind of interesting to remember, because I remember he had asked a question about your fluidity of membranes, and I thought that maybe he's going to come back to this idea. And I remember that your test question was on the fluidity of membranes. Remember, he was talking about that. And as the temperature decreases, the membrane remains fluid to lower temperature if it's rich in phospholipids with unsaturated, right? Unsaturated still will move in lower temperatures. But if it's saturated, then actually right? You know about that part, right? When you cool something that's saturated, it becomes solidified like butter. Anyways, I just wanted to make sure I didn't forget about the cholesterol, since there's a picture there on this. Okay. Yeah, we might. I'm gonna make this an important thing to add on membranes and these. I didn't do that well enough. That was my mistake. We'll go back to that. Okay. So the H ions flow down the gradients, enter a channel in a stator, which is anchored in the molecule. The rotor and the H ions complete one turn, spinning the rod and activating ATP. Oh, that's all fucking garbage. All right, who cares? And then, all right. We talked about collecting the ATP. Okay, fermentation is really important. Without the electronegative oxygen. So sometimes, what if you didn't have oxygen, or the cell's running out of oxygen? Can you still function? Can still be a cell, meaning that, let's say, the cell's not getting oxygen for some reason. Maybe it's the heart's too sick, and the heart can't pump enough, or you're drowning in water, and you don't have oxygen. Will you immediately die, or how will the cells work without oxygen, right? And so without the electronegative oxygen and atoms that pull electron down the transport chain, oxidative phosphorylation will stop. Right? You can't do electron transport chain, right, that pull the oxygen down. However, there are two general mechanisms by which certain cells can oxidize without use of oxygen. Okay, that is electron transport is using anaerobic anaerobic respiration. The electron transport chain is also called the respiratory because of its role in both. I don't even know what that means. We've already mentioned anaerobic respiration, which takes place in prokaryotic organisms that live in. They don't have. So oxygen forms the wells. It's two electronegative enzymes. Okay, I don't know what we're talking about here. Fermentation is a way of harvesting the. Okay, don't worry about that. The glycolysis. That's what I say. Remember, oxidation simply refers to the loss of electrons. So it does not need to have oxygen, right? Glycolysis can occur without oxygen, right? You can make glycolysis into pyruvate, right? So the oxidizing agent of glycolysis is NAD. So and neither oxygen nor electron is involved. So NAD does all the work, right? So glycolysis is exergonic. It does produce 2-ATP. Okay, now, if oxygen is present, then ATP is made by oxidative phosphorylation when NADH passes electrons removed from glucose to the electron transport chain. Now, but glycolysis generates 2-ATP when oxygen is present or not. So glycolysis always produces 2-ATP regardless. It's what happens at the NADH is the whole point, right? Meaning if oxygen is present, NADH can do something. Right, now, the problem is if you keep building up NADH and don't use it, it's going to be a problem, right? You got to regenerate the NADH. So this is where fermentation is. Fermentation is the process of regenerating NAD. Remember, if glycolysis keeps making NADH, you're going to run out of NAD, right? But transferring, so that's going to be a problem. The NAD can then be reused, so you got to create NAD back. So you got to do NAD regeneration. That's the critical part of a fermentation, right? So you got your glucose, make your ATP to make the pyruvate. Remember the carbon dioxide, the 3, and then you pop the head off, and you get the carbon dioxide, and you get an H off. You get the 2-acetylaldehyde. And it's this generation here, it goes from here to here to 2 alcohols. 2-acetyl to 2 alcohol, that alcohol fermentation. Remember, alcohol fermentation actually makes carbon dioxide. That's why beer is very gassy, or alcohol is very gassy, because it's carbonated. Look at the carbon dioxide, and look at the alcohol fermentation. So you're actually making NADH from the glycolysis, ATP, but now the NADH, which is not being used for anything, unless you had oxygen happening. Then you could go over there and deliver it to the oxygen transport train. But since there's no oxygen, NADH really serves no purpose. It does nothing. NADH has to be delivered to the electron transport chain, or to be purposeful, primarily. because it is on the outside. It's in the glycolysis area. The NADH of the glycolysis is not involved in the citric acid cycle because it's not delivering. It's impermeable to the membrane. Remember that part? It's impermeable. So then the NADH just sits outside and just keeps doing this. Glycolysis, alcohol. Glycolysis, sugar, alcohol, sugar, alcohol. Now that's not what happens in us. That happens in yeast. Okay. Alcohol fermentation is bacteria do that, and yeast do that. Okay. And that's why you get carbon dioxide generated. That's why. But in us, we do lactic acid fermentation. We glycolysis 2-pyruvates. Remember, the 2-pyruvates turn directly into lactate. Now, what about lactate production in humans? It was thought that lactate is bad. Oh my God, lactic acidosis. But here it looks like that you don't make carbon dioxide when you make. You don't cut the head off here when you make lactic acid. Lactates don't make carbon dioxide. Alcohol makes carbon. So we don't make beer. We make lactates. Okay. The lactate products are most often oxidized in the vicinity. We basically end up storing lactate as glycogen or different things. It's stored for glucose formation later on. So when carbohydrate metabolism outpaces the supply of oxygen, then lactic acid can't be oxidized to pyruvate. The lactate, when carbohydrate metabolism outpaces the supply of oxygen from the blood to the muscle, lactate can't be oxidized to pyruvate. The lactate then accumulates to cause muscle fatigue. Okay. All right, let's compare fermentation with aerobic and anaerobic respiration. So key difference in contrasting mechanisms, oxidizing, which requires sustained glycolysis. In fermentation, the final electron receptor, such as pyruvate or acetaldehyde, right? It's acetaldehyde before alcohol, or it's pyruvate in us. Cellular respiration, electrons carried by NADH, we know, go to the electron transport chain. That we're very clear on. In fermentation, the electron is pyruvate. They're the final electron acceptors, the NADHs. The NADH can only deliver, right? The NAD here is giving sorry. The NADH, the NADH is delivering the electrons to this. So NADH is actually giving electrons to pyruvate. That's the whole point here. NADH is giving electrons to pyruvate to create NAD. So the NADH is actually giving these guys the electrons. Remember where we were before, NADH is giving electrons to the electron transport chain. Here, NADH is giving electrons to the pyruvate under fermentation. That's what's going on. NADH is giving electrons to the pyruvate to then, when it gives the electrons to the pyruvate, you end up with your NAD+, which then goes back to glycolysis to pick up the electrons from glycolysis where NADH was made. But since now the NADH, which remember normally made in the glycolysis, remember glycolysis normally makes NADH. Now that NADH, in this circumstance, is actually going to go on to NAD regeneration to the 2 lactic acids. So 2 lactic acids are made when 2 electrons are given to 2 pyruvates. So 2 pyruvates pick up 2 electrons from the NADH to make the lactic acid. So pyruvate is a form of lactate, but it's due to picking up of the electrons. That is fermentation in itself, concept that may or may not show up in your test. But I think it's a very important concept that you will need to remember for a long time and forever. It's a real important concept. That is the idea. Okay, so key difference in contrasting mechanism for oxides. My God. Fermentation yields 2 molecules of ATP produced by substrate level phosphorylation. Bottom line is what they're trying to say is that this is substrate phosphorylation was glycolysis. And that's 2 ATP. That's the same thing. Is that fermentation does produce ATP, but that's basically because of glycolysis. Now, in the absence of electrons, the energy stored in pyruvate is unavailable. In cellular respiration, pyruvate is completely oxidized in the mitochondria, right? So we actually never use the pyruvate for any energy in fermentation, right? It just becomes lactate. So you really never use it. You only give electrons to the pyruvate, so pyruvate itself doesn't do anything. Where versus in regular respiration, cellular respiration, pyruvate goes on and travels into the citric acid cycle in a whole and gets involved. And here, poor pyruvate doesn't get to do anything because there's no oxygen out here. So it just hangs out here and won't get involved in anything else. So 2 molecules are 8. So major difference is that fermentation yields 2 ATPs produced by substrate level phosphorylation, which is basically that we say. And then the absence of electron transport chain, the energy stored in pyruvate is unavailable. In cellular respiration, okay, most of the chemical energy is shuttled to NADH, we talked about that. Stepwise, so cellular respiration generates much more energy. In fact, aerobic respiration does 32 molecules of ATP, okay, up to 16 times as much as fermentation does. Now, some organelles obligate and carry. Okay, so anyway, the key difference, that's an important concept. All right, that hopefully you really now appreciate this better. Going back to this again, glucose comes in, glycolysis happens. Pyruvate has 2 choices. It can go here if oxygen is present. It can go on to become acetyl-CoA. Remember, it has to cross through an electron transport chain. That electron it has to be taken up actively, right? If oxygen is not present, it goes on to fermentation to make lactic acid, lactate. Okay, the pyruvate is a key juncture in catabolism. So pyruvate can go either way. Remember, pyruvate here does nothing. It goes on to become lactate. Or pyruvate goes here and goes on to the citric acid cycle as acetyl-CoA. And then, so remember, they were generating a lot of things here. A lot of NADHs were being generated through here, which then traveled inside here to electron transport chain, right? So that's the key point of the difference between fermentation and when the oxygen is present, not present, okay? Okay. Also important to know, we're almost done. I can't believe it with respiration. Let me pause this so I don't keep uploading videos. Okay, we're going to take a quick break.